Bonjour tout le monde. J'espère qu'il y a beaucoup de monde qui nous suivent en ligne. Donc aujourd'hui, nous avons l'honneur de recevoir la professeure Alix Munier-Kordon de l'Université de Paris 6. C'est ça? Paris 6, Paris Nanterre, de Sorbonne, c'est l'île 6, n'est-ce pas? OK, voilà. Et donc, Alix est professeur alors, donc, est professeur à l'Université de Paris 6. Elle est spécialiste en recherche en optimisation combinatoire. Et puis, elle va nous présenter ses dernières recherches sur ce thème-là. Six parameter tractability of scheduling dependent type tasks subject to release time and deadlines. Voilà. Merci de ta venue, Alix. Et puis, tu as la parole.
Merci, Janet. Yes, this is a joint work with Claire Hanen from Université of Paris Nanterre. So, the outline of my talk. First, I will present the scheduling problem that we are talking about. Then, some few words about what is the challenge of the parameterized approach concerning this scheduling problem. And I will treat heavily, I would say, the case of the unit time processing time jobs, which is a very simple case, but which allows to understand what kind of algorithm we developed. And then I will continue with the complexity when the problem when the processing time of the job is not unitary, and then I will finish by some extension and some reference. So just for the beginning, as input, we consider a usual scheduling problem. It's composed by a set of tasks. We have on tasks or jobs, which are non-preemptive. It means that we cannot cut them, preempt them when it is when you decide to do it, you do it totally. Each job has an integer processing time of pi, and we have also release times and the deadlines. Here in this small figure, we represent the time windows of each job, which we start with the release time and end with the deadline. And here we have and each job has a certain processing time as it is presented here, and of course it can be placed in the beginning or in the end or in the middle of its time window. Usually, we also consider precedence constraints. Precedence constraints, it means that, for example, you have a precedence constraint between these two jobs. It means that you can start the task 2 when the task 1 is completely finished. So it's a usual definition of precedence constraint. And the precedence graph, which is a directed acyclic graph, is an input of also an input of the problem. If we consider only the jobs in the time window on the precedence graph, finding a feasible schedule is a very easy problem. So usually, it is difficult if we consider resource limitations. And here, as resource limitation, the more general kind of resource we consider is that what we call type task. Type task means that the processor are divided into classes. So we have 5 classes of processor. For each class of processor has a certain number of identical machines, which is also fixed. And each job has to be processed by a given machine type. So the, just as an example here, I consider two classes of machine. One is composed by one machine, the other is composed by two machines. And when we define the class, we know for which kind of machine he has to consider. For example, here, such one surely has to be executed on machine type 1. 4 and 5 of type 2, it is given as an input. It is not you that you choose, it is just given as an input. And the problem is to find, if possible, a feasible scale. In fact, it is a decision problem. There is no optimization criteria. It is just a decision problem. And usually we note it like this. Do you know gram notations? Do you know it? So the gram notation is a three-field notation. One field, second one, third one. The first field usually describe the kind of machine or the kind of resource you have. Here, when it is P, it means it is parallel process. Then here you have a second field which can be quite long with keywords to describe the problem. Here, this keyword is not a usual one for scheduling practitioner. Means that you have type system. Here means you have precedence constraints. Here means that you have release time, you have deadlines. On the third field usually considered is for the optimization criteria. Here we do not have optimization criteria, so we put a star. You see, it's only a decision problem. It is not an optimization problem. So just to finish with this problem, before next section, if I consider the scheduling problem, it is an hard problem. It was proved by Janssen a few years ago, and it is hard even if the processing time are equal to 1, and there is no release time on the blocks. So it's a difficult problem. And usually, people that are working on operation research, we consider that we have to study the complexity of the problem. When the problem is difficult, usually we develop exact methods like branch and bound methods, or to have exact solution, or develop heuristics or meta heuristics to have good solution. On this top here, the study of the complexity. So the parameterized complexity is a way to go a little bit further to study the real complexity of the problem. So what we do? First, we add a parameter. We say, okay, we know that the problem isn't hard. So now, can we say something intelligent if we know that some parameters are bounded? So first, we have to choose the good parameter. And I will say it's an art to find the good parameter and to imagine that the problem will become easier if this parameter is bounded. It is already. And the people working on scheduling problems during a long time do not interested in this kind of problem, since I was probably after, but we have a lot of difficulties to find good parameters that will simplify the theoretical complexity of the. Vous pouvez m'interrompre si vous avez des questions. Okay. So what is the parameterized complexity? In fact, people are working on parameterized complexity start from the definition of P on NP. You know, polynomial problems are included into NP, and we know that The more difficult class of problems in P are called NP complete. This is the base of the NP complete. Here we have the same theory, but the easier class is what we call FPT. And we say that the problem is FPT. FPT means fixed parameter tractable. So you have a problem and you have a parameter. You decide the parameter. So the problem is of size n, and your parameter, the parameter is called P. And we say that a problem is fixed parameter tractable if there exists an algorithm with type complexity is of this form. Means that here you have a function of the parameter multiplied a polynomial on n. So the meaning here is that if k is small, in fact we have a polynomial time complexity for, of course, an half of okay. So this, when it is possible, it is the best that we can imagine. And in this case, we are here. Then we identify that in a lot of cases, when the parameter probably is not as good as we can imagine, or the problem is very difficult, we are not able to find this kind of fixed parameter. So the people working on this theory imagine bigger class and identify a lot of classes. And in fact, when I see here, we have several classes: W1, W2, WSAT, WP. It is complexity classes. I won't detail it. It's not the objective. But there are many complexity classes, and they are all include each other. Okay, and there are two overall classes of more difficult problem. It is the para-NP problem and XP problem, which are two. And these two classes, the intersection is not empty, but they are not included one each with the other. So when we have a problem, the goal is to find if the problem is a problem with a parameter, if the problem is a fixed parameter tractable, and if it is not, we have to find where we can put it in this hierarchy.
Just W1, what does it mean?
W1, it means that there is a transformation with one problem, which is very similar to SAT. It is logical problems. These parameters, in fact, correspond to several layers of the problem. It's long to explain, but what it is important here is to understand that they are all include one each other. I won't detail it since I don't need it for this talk, so I prefer not to detail it. It can take time. Okay. So just have a look in the literature. In fact, when we are looking to the people working on this problem, we found that several parameters were considered. The easier one, we say, was the Cmax. It is not well. This comes from graph problems. Since in graph, it is usual to consider as parameter the size of the result. So since people working initially, people who are working in this class of problem comes from graph theory. So these parameters seems for them a good parameter. Even for people working on scheduling, I see Pierre is, yes, it's not, for me also it is not a good parameter, but it exists, I would say. Other parameter is the number of machines, the maximum duration of a task, or the slack. The slack is the maximum deviation if you consider the earliest starting time. Or the width of the precedence graph. The width of the precedence graph is if you look the precedence graph, is the number of tasks that are independent, are not that are with no relationship. And we have there are a lot of negative results. For example, if you consider the parameter the duration of the schedule, then if you look very old results from Lenstra and Munier-Kordon, these two guys proved that this problem, if Cmax, if the duration is less than 3, the problem is incomplete. So it means that it is the definition of para-NP hard if we consider this value. Since it is difficult if the duration is 3. So the length is not a good parameter, since even for a small value, the problem is NP hard. So this is the definition of para-NP hard. If we consider that yes.
Okay.
Come on.
It's para-NP hard for this parameter.
Yes, for this
parameter.
parameter.
For another one.
Yes.
Okay.
Yes.
You can try to find another parameter.
Yeah, it means that the parameter is not good.
Yeah, that's all.
Yes, but it is interesting.
Yeah, it's an information.
It's an information.
It's not an information, the problem.
It is the problem with the parameter. Yes. It means that the parameter is not good. Yeah. More interesting. If we consider the width, so the width is the number of independent tasks. Then this problem, 2 machines, precedence constraints, the duration equal to 1 or 2, and the Cmax. This problem was found to be W2 hard. It means that difficult. It is not FPT. And it is a recent. It is a very recent. So now, if we consider both the width and the Pmax, so we have a couple of parameters, the problem is still difficult. So even if you consider the 2 parameters, but if we consider this is interesting. If we consider the width and the slack, then PS means that RCPSP. RCPSP means that it is not type task system, but in this case, it is you have several types of machines, and the task can need several machines of several types. It's a quite general. It's a very general. If you consider only the precedence on this kind of machine, and you want to minimize the next time, then you have a FP. And it's a very interesting way. It's a very interesting result, and I will say it is the first positive result for this class of problem. So if you have any question, feel free.
And they really have a polynomial algorithm for this problem.
It is polynomial.
If you know the bound.
If these two values are bounded. Yes. Yes, it's polynomial. It's a very interesting. It's a very interesting approach on the structure of the precedence graph. Now, another parameter is what we call the pass-width. I will say it is our favorite parameter. And our favorite parameter is when we consider this time and deadlines is the number of tasks that can be done simultaneously. And just it is not seen in this scheme, but here it's open, so we do not consider this data. So here the maximum number is 5. And then we have several positive results. So the first one that will present deeply here is when we consider M identical machine, precedence constraints, task of duration 1, release time and deadlines. Then we have a fixed parameter algorithm to solve it. If we consider only the same parameters with two machines, but with no constraints on the duration, then this problem becomes parameterized. But if we consider both the pass width and the minimum between the duration, so the maximum duration and the maximum slack, then in fact we can extend this algorithm to this class of problem, but with an additional parameter. Okay. So now we are going to see how this works. So in fact, how this works, for this, I will develop an exact algorithm, which complexity will be on this form. So here, we have a polynomial in N, and here we have a term on the pass, which a function which can be very huge, but on the pass width. So it means that if the pass width is small, you have a polynomial.
It is a constant.
Yes, yes. If mu is constant, it is polynomial.
So it's always polynomial.
If mu yes.
Even if mu is big, it's polynomial. The question is that it can take a long time because the coefficient is big.
Yes, it can take a very long time.
Yeah.
So the corollary is then, in fact, it means that this algorithm can be considered to solve optimization problem. To do it, we consider binary search. Binary search is not the good. It is not in fact the good answer for this problem, since it can be better. But if we are lazy, we can say that okay, since we have FPT algorithm for the decision problem, we can extend it to optimization problem using a binary search. It's easy.
Yes, we don't have here the deadlines.
Hmm? No, but you can remove them.
We can remove the deadline
because of the since in fact you can put it or remove it. Since the deadline, in fact, you compute the deadline using the bound on the expansion. So you can remove the deadline. It's not a problem. You can put it or remove it. Okay. So how it works? Just so let's consider an instance of our scheduling problem. So we have a precedence graph, and we have for each task we have release time on the date. The problem here is to find if there exists a feasible solution. So the answer is yes, no. So what we will do, we will first how we compute the pass width question. We define the sequence with an important role. U alpha. U alpha is the instant when something occurs here. So the smallest one is 0, then 1, 2, 3, 4, 5. All the rest. But here in this example, you have every integer that you can skip. You can have a slice, in fact. And then K is the number of terms of the sequence, kappa. And X alpha is the for alpha in 1 in kappa is all the tasks that can belongs in this slice, that can be executed in this slice. Okay, so for example, so for this definition, I don't need the release time, I don't need the graph, in fact. But sometimes, release time on the lens can be computed using the graph. Here, I just consider the graph. For this value, I don't need the graph, but on the on these sets are defined only with this definition. So here, x1, so there is only the first pass. x2, sometimes x2, I can have the one, the task 2 and the task 4. x3, the task x3 is between 2 and 3, 3 and 4, no, 2 and 3, 2 and 3, the task 1 is removed, etc., etc. And the pass with, in fact, is the number. Just to be clear. Sometimes we say that the pass with is 3, the number of tasks of it, or sometimes it's 3 minus 1. It's equivalent. Just, in fact, when the pass with is not why we call this value the pass with, it is because if you consider a graph correspond to the definition in the graph for people working on graph theory on the pass with, which is the pass with is a way to decompose a graph into a pass. In fact, when you have a graph, and you want to see if your graph looks like a pass, we have some transformation to transform a graph into a pass, and the size, the maximum size of node that you have to put in the same value, we call it the pass width. And in fact, here it is exactly the same notion, so that's why we call it a pass width. But here, in fact, the pass width, if you consider graph theoretical definition, it is this value minus 1. So it's a detail.
X3 or just for this case?
For this case, it is X3.
Why is it X3?
X3 is the biggest.
Ah, okay.
This is the biggest subset.
Okay.
Okay. Now, let us consider to see how this can be. Let us consider first a feasible schedule. This one is feasible. Just trust me, it is feasible. Here we have the sentence, the sequence U alpha, and we will define the slice. The slice is just the task between two consecutive instants of the sequence U alpha. In fact, here we have one slice here, the second one slice here, one slice here, and one slice here. You have put it here. And in fact, a very simple way to store this schedule is to say, well, in fact, we can store this schedule as a pass in the graph. And at the beginning, the set is empty. Then the set is S1, so this. Then the second node is only this. Then the third node is this part, this pass, etc., etc. So each node represents a set of tasks that are executed here during this time, here during this time, here during this time, etc., etc. And in fact, we put an arc if we can go from an instant to the other instant. And it is quite easy. In fact, if you go from here to here to build the schedule, this pass represents this schedule. But now, the problem is that what is the side of the nodes? Is it possible to do something intelligent? So the idea of the algorithm simply will be to say, well, I'm going to build a state graph where each node will be a set of tasks that are executed from U1 to U alpha. So at the beginning, and important, V alpha is the set of tasks associated to a schedule to U1 to U alpha. So these states are partitioned into several subclasses. Okay. For example, if I consider here the first schedule, here we have V1, V2, V3, V4, V5. Okay. And okay, so the algorithm simply put at the beginning the empty set to V1 corresponding to S, in fact. At the beginning, the number of the edges of the state graph are empty, and the number of nodes of the state graph is only this empty the nodes corresponding to the empty set. And then for every value alpha, I will build all the possible nodes, and when I get a node, I will see. Just so at the beginning of just one nodes, I will build all the nodes. So it will be quite numerous number of nodes, and I will see if some of the nodes can be connected to, and so on. And I will build this graph, and I will just existent arcs. We just see if an arc is possible. Okay. And then, if there exists a path from S to a terminal node means all the tasks, then it will be associated to a feasible schedule. So the answer is yes. If there is no, the answer is no. Okay. Now the question is, what is the complexity of this kind of algorithm? Then everything is in the representation of units. And then for that we will define another set, which what we call Z alpha. Z alpha is the set of nodes, set of tasks for which the deadline is less than U alpha. So for the example, at the beginning we have empty set, and then this set is increasing as soon as the nodes have to be finished. And then there is an interesting property, is that when you consider a node, and you have a look at the task represented by this node. This node necessarily belongs to the alpha, since the partition belongs to the nodes. Then you notice that the tasks of this associated to these nodes belongs to, some are belonging to Z alpha, and the other that are not belonging to Z alpha necessarily belong to X alpha. So just an example, here I put for small example the nodes, the task included in the alpha. For alpha from 1 to 6, it corresponds to the path I saw here. The X alpha corresponding. So for example, if I take alpha equal to 4, this is all the tasks that are in the V alpha. But in fact, it includes tasks from the alpha and the 1 to 4, and the remaining tasks 3 and 5 are belonging to itself. Okay. So this the consequence is that when I will build all the tasks, for example, from 2 to 2, I will consider only the tasks from X2. I do not have to need, I don't need to consider tasks from Z2 since they are included in it. And so each node is only represented by this subset. And clearly, this subset, as we see, is included in X alpha. So there is at most new the pathways task to consider to build this node. So in consequence, the number of nodes is bounded by this function, since you have all the by all the possible subset of X alpha. In fact, there is two new, and we can also quite easily, but I won't prove that the total number of arcs is also bounded. Since the arcs only correspond to nu alpha plus 1. So it is also bounded by this kind of function. So just to have a look at, for example, you get this kind of graph. This is the path that we show, and there are also several other ways to go from the beginning to the end. So, and here we only represent the task from X alpha, not from Z alpha, since we know they are included. Okay. So the last thing is just to deal with the complexity of the function exist arc. We know that the number of arcs is limited. But in fact, well, I won't detail it, but the complexity of the number of the existence of an arc between two sets of this kind of and so this can we conclude that our algorithm has this complexity.
And it is a maximum.
It is, yes, it is an upper bound.
It's not necessarily
rigid. It is clearly an upper bound.
Yeah,
it was heavily upper bounded.
So you simultaneously have an algorithm that can be much more efficient.
Yes.
Yeah.
You can imagine. Yes, that's it.
That's fine. It's fine. It's simply hard.
Yes.
And you solve it in a linear time.
Not linear, but in polynomial time, if it is bound. But it is the parameterized complexity. Okay, so if now we consider not unitary duration. In fact, we start from a sub-problem of partition for which it is partition, but you have 2p integer values, and for every g, this one is strictly inferior than the second one. So this relation relies only two couples of partitions. Yeah, sure. I'm not clear.
Maybe you're clear, but I don't understand. Which is another problem.
It is very so. You should be able to understand. So you have this is the successive value of partition. And what is saying is this one is less than inferior than this one. This one is inferior than this one, etc. And then at each time, you have just, when you will build your instance of partition, you just have to consider bicouple. And one on the first machine, the second on the second machine.
What do you call a partition?
The partition problem. Partition problem, usual partition problem. You have values, and you have to put this value into subsets, and such that when you sum the values of the first subset, it is equal to the usual partition problem. Here it is a usual partition problem, but what you want is that these two consecutive values are not in the same subset. And this one also. And this one also. And this value is strictly less than this value. This one is strictly less than this one, etc. So it is a very
special
partition problem. And what is funny, it is a problem is P complete, even with it. But what it is funny, it is right in the Garrett-Johnson. This is NP complete, no proof, no reference of the proof, nothing. Since probably they found it is very simple. And when we put on the paper, Garrett-Johnson claimed that this problem is NP complete. And the reviewer, when he saw our papers, where it come from? So it's the claim. So they ask us to prove this problem. In fact, the proof has no interest, but it is they were right. And I imagine that they found it was so simple that they do not even give the proof, since these two authors consider it was evident.
Obvious.
It was obvious. Honestly, the proof is not difficult. We can discuss after if you want, but effectively, this problem is effectively NP complete. And we will consider this problem to prove that this problem is NP complete. So there are two machines, release time, deadlines. No, and just is there possibilities to there are feasible solutions. There are no assumption on the processing time, but we have a pathway bound. But in fact, this is quite the proof is simple. We can discuss it. But what we have to say is that when we look at the complexity proof concerning scheduling problems, usually the author consider a very small make span, so a make span of 3, as we see, for example, Lenstra Renault plan. So they consider a very short make span with very huge pathways, of course. But here we have to do the contrary. We have to spread the schedule, but with a very small pathways. And this problem, essay partition, is the good candidate. Since in fact, well, I won't detail the proof. It's not so interesting, but the idea here is in fact to consider task with duration with value, but adding some stuff to have in fact a release time and deadlines like this for the two first value, like this for the by spreading the problem. And then the pathways is very short, but the duration is quite long. It's not a problem, and we can transform then this problem into a problem like this point. And this allows us to prove that this problem is NP-complete. And the consequence, if you then look the definition of para-NP completeness, it means that the same problem parameterized by the pathways is para-NP complete, means that no way to consider only this parameter to get a FP10. Okay. So just to finish, skip this one. In fact, we want FPT for this. So what we do, we add another parameter. We added as other parameter, for example, the maximum duration of the task. And briefly, we extended the previous approach. We extend by, in fact, here I just represent a slice of schedule. If you look at a slice of schedule, in fact, you have U alpha and U alpha plus 1 defined as we see. In fact, there will be several kinds of tasks. There are the tasks, and there are tasks that are crosses the borders. And in fact, what we do when we build the state graph, we will consider all the tasks that are finished. So all this one, but we will add what happens on the border. And in fact, what happened on the border, the combinatorial is not so heavy. Since you just have to pmax position for each task. This is why this term occurs, in fact, in the scheme. Okay. So just to so the two main references in this book are two people that are this one for the processing time equal to 1, this one for the general problem, and the complexity study with partition, and just some recent work on this class of problem. We extended this approach for problem with communication delays. We also consider here in this paper length on the precedence. And in this paper, we show that some branch and bound algorithm considered for usual parallel relation scaling problem can be seen as a parameterized algorithm, considering both the maximum duration of the task and the pathways. Okay. Just to conclude, well, I feel that the study of the parameterized complexity for basic scheduling problem is a wide open field, since there are very few results, in fact. And I think there is a lot of things to search in this way. We are also convinced that this couple, the pathway with Emacs, is a very good parameter, since we can, in fact, develop a FPT algorithm for problem considered for scheduling theoretical and practitioner as very difficult problem. So it seems to be a good couple of parameters. And we feel that, in fact, the state graph you are not necessarily have to build systematically all the state graph, since you can, by adding dominance properties, you can filter the good states and probably be intelligent in the construction of the state graph. And of course, we are also looking for more interesting parameters, and we have some ideas about this. So, thank you.